Okay, hello everyone, and welcome to our first guided notes of the semester. You're going to notice that my copy has a little bit more on it than your copy. This is not typical, but this first time through I have added some points onto the graph and given a few extra instructions over here in the white space. So if this is not already present on your copy, go ahead and add it in. I've added up here in red, you are in control. The great thing about a flipped class where you have the lecture part in your guided notes is that you are absolutely in control of the speed. Feel free to pause and rewind whenever you need to. That means I'm going to probably talk a little more quickly, go through the points a little bit more quickly, and I'm recognizing that I've got crazy nails on for this first time. I apologize if that is a distraction to anyone. It's summer while I'm recording this. Okay, so we're going to start out with hopefully a review of graphing lines and of the Cartesian coordinate system. Now, you may not have heard it called the Cartesian coordinate system before, but you've used this, this graphing format before. This Cartesian coordinate system has two axes, a horizontal x-axis and a vertical y-axis that divide the plane into four quadrants. Now, we have just pictured a small piece of the plane. We think about the plane extending forever in all directions as a flat surface. We have our two axes that meet at right angles at the point we call the origin, O-R-I-G-I-N, the origin there at 0, 0. The first quadrant, 1, Roman numeral 1, is at 1 o'clock on the clock, but then I go counterclockwise to number the others. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now you're going to notice, for example, point A is in quadrant 2. When I give the coordinates, I'm giving an XY ordered pair. X is my dependent, or excuse me, X is my independent variable, Y is my dependent variable, and it always has to be in this order. That matters. So if I'm looking to map the location for point A, I'm going to say that A is at -3, 2, because that is my X coordinate and then my Y coordinate. Quadrant 2, every coordinate in quadrant 2 is going to have a negative X value and a positive Y value. In quadrant 1, where B is, every coordinate is positive. Positive X, positive Y. So I can see that B is at 2 on the X-axis, and then I go up to 4 on the Y-axis. So the location of point B is 2, 4. C is in quadrant 3. In quadrant 3, I can see that I'm in the negative quadrant for both X and Y. Both the X and Y coordinates are negative over here in quadrant 3. And in quadrant 4, I'm back in the positive coordinates for X, still down here in the negatives for Y. So go ahead and pause the video maybe, fill in the coordinates, the location mapped, location spots for point C and point D. Order absolutely matters with these coordinates. It's always X, then Y. The last two instructions for this part, place point E on the X-axis. This X-axis is my horizontal axis. I can put point E anywhere I want to on that horizontal axis. It makes absolutely no difference. I'm going to choose to put point E right here. My coordinates for E are going to be 4, 0. The Y coordinate is 0 because I'm on the X-axis. I haven't moved up or down. If I put point F on the Y-axis, I'm putting it somewhere on this vertical axis. I'm going to choose to put it down here at -4. So point F is here. The coordinates for F are 0 because I didn't move left or right. I'm still on the Y-axis. And then my Y coordinate is -4. So anytime I'm on the X-axis, I will have some value. We're going to say C for a constant, 0 for the Y coordinate, because I'm on the X-axis, I'm not moving up, I'm not moving down, so that second coordinate is 0. If I'm on the Y-axis though, my first coordinate is 0 because I'm not moving up or down. No, I'm not moving left or right. You're going to figure out that I misspeak. I make mistakes. The problem with videos is that there's nobody here to catch my mistake if I don't catch it. So just let me know if you find a mistake that I didn't catch, and I will make a note about it in Canvas. Okay, let's move on to our next section here. Is the given ordered pair a solution to the equation? Well, how do I know if I have a solution to the equation? I've got a solution if I'm able to plug in the x and y values. Then I see if it gives me a true statement. So what I'm asking here is, would this point be a spot on the graph? Would it be a point on the graph? And we know that by thinking about what would happen if we graph this equation. This equation is going to be the equation for an ellipse or a circle. It looks like it's going to be a circle because I don't have any coefficients out in front. I know it's a circle. You don't know it's a circle. Don't panic if you didn't know that. I know it's a circle because I have an x square and I have a y square. So when I have an x square plus a y square, I know I'm going to have a circle. So the question is, does the circle go through this point 3, 4? If I put the circle on my graph, is one of the points on the circle going to be 3, 4? Well, to check that, I plug in 3 for x and 4 for y, and then I use order of operations to solve. 3 minus 2 is 1. 4 plus 2 is 6. And I can see right now that's not going to be a true statement. 1 squared is 1, 6 squared is 36. 1 plus 36 is 37, and that does not equal 6. So no, that is not a solution. Make sure you answer the question, yes or no, when it asks if something is. So no, this is not a solution. What about over here? My equation here doesn't have anything squared, it's just x and just y. That's going to be a line. Let's go ahead and make notes of these. This would be a circle, just interesting information to know because I have x squared and y squared. This would be a line, and we're going to be graphing lines today because it's just x and y, no coefficients or anything else going on. Let's plug in our values and see if 1, negative 3 is a point on this particular line. So I plug in 1 for x, minus a negative 3. Got to watch those negatives. If I'm going to have a problem, that's where I'll probably have it. Well, 3 times 1 is just 3. Minus a negative. This is like saying a negative 1 times a negative 3. That becomes plus 3. 1 times 3 is 3. A negative times a negative is a positive. Minus 6 equals 0. Is that a true statement? Well, yeah, that is. 3 plus 3 is 6. And 6 minus 6 is 0. 0 does equal 0. So the point that I was given is a solution to that equation. Okay, let's look at this bottom part. Graphing linear functions using intercepts. So as I look at this one, I'm sorry, I've rearranged some things on my notes. I want to make sure that I get everything included that I wanted included. This line, and we're going to think of this as a line. We need to go ahead, I don't know why I did not pay attention to that before. That should be extended so that I see the line goes on forever in both directions. As I move from left to right, like you read a book from left to right, you read graphs from left to right. So as I move from left to right, my line is going up. That means that I have a positive slope. And this line, as I move from left to right, my line is going down, it's decreasing. I have a negative slope. So let's think about what's happening here. For function 1, this is function 1 right there. Let's kind of color code this some. For function 1, my x-intercept is where I hit the x-axis. That is right here at negative 3. So x is negative 3, y is 0. That's the location of my x-intercept. My y-intercept is where I intercept or hit the y-axis. That's up at 1, 2. So I haven't moved left or right from center, so I've gone 0 and then up 2. That's my y-intercept. And then when we look at function 2, that is too close to the same color, so let me find a different color here. Let's see if this color shows up for me. That's not bad. There we go. Orange will work. So for function 2, my x-intercept happens over here on the positive side. 1, 2, 3, 4. So 4 and then up and down 0. My y-intercept is over here. I haven't moved left or right from the origin, so that's 0. Then I went up 1, 2, 3. So what do you notice is true about both of these functions, function 1 and function 2? For my x-intercept, for both of these values, my y-coordinate is 0. So I have some x-coordinate and then my y-coordinate is 0. That's always going to be true when I'm trying to find my x-intercept. For my y-intercept, however, it's always the x-coordinate that is 0, and then I have some value for y. So if I'm going to try to find my y-intercept, I'm looking to see where x is equal to 0. And those are going to be true things that we're going to do for every type of graph, every type of equation that we have, trying to find x and y intercepts. Let's look at the next page. We're going to use intercepts to graph these functions. Well, we just said that to find these intercepts, what did we say? We said to find the x-intercept, we set y equal to 0. And to find the y-intercept, we set x equal to 0. So these are true statements that we're going to use all semester, every part of our math journey. Okay, so if I want to use intercepts to graph this first function, first I'm going to stop and I'm going to look at my equation, and I see that I have x, I have y, no exponents, nothing else funky going on. This is going to be a line. This is going to be a linear function. So I'm looking at a straight line. What happens if x is 0? Well, if x is 0, right here, I have 3 times 0 plus 4y equals 12. Well, anything times 0 is 0. So that just is 4y equals 12. And I need to solve for y. 4 times y, I need to do that inverse or opposite operation. So I'm going to divide both sides by 4. And I get that y would be 3 when x is 0. So that is my y-intercept. Happens when x is 0. For this graph, y will be 3. So where x is 0, y will be up here at 3. All right? What about the that's the y-intercept. How about the x-intercept? Well, for the x-intercept, y is 0. So when I plug a 0 in for y here, I have 3x plus 4 times 0 equals 12. Again, anything times 0 is 0, so that's the same thing as just saying 3x equals 12. 3 times x, the opposite of multiplying, the inverse operation of multiplying is division. So I'm going to divide both sides by 3, and I get that x would be 4. So for the x-intercept, x is 4, y is 0. So x is 4, 1, 2, 3, 4, y is 0. There are my intercepts, and I can use those to graph my system. And I forgot to grab a straight edge. Let me see. Here we go. All right. And there is my line. I see that my line has a negative slope. A line with a negative slope. All right. So pause the video. This is that first time to give you that chance. Pause the video and graph this equation by finding the x and y intercepts. Plug in for x-intercept, plug in 0 for y-intercept, plug in 0 for x, graph them, and graph your line. I'm going to go ahead and do it real quickly. So pause the video, take your time, work it out. Make sure that you get the same thing I do. My y-intercept where x is 0, I get negative 6. Now I'm not showing me working it out, but I did. I put those things down on a piece of paper, figured it out. I plotted the points to 0 and 0, negative 6. Any 2 points connect to make a line. And I see that this line has a positive slope. All right, that moves us right into our next section. Now, This video is just a quick and fast. We're introducing the concepts. You can slow it down, you can rewatch as many times as you want, but we are just introducing concepts. And then in class we will practice those concepts. Bring your completed guided notes to class every day so you'll have them to ask questions about and to reference. Slope of a linear function. Okay, we've already talked about positive slopes. As I move left to right, I'm going up. We've talked about negative slopes. As I move left to right, I'm moving down. That's positive slope, negative slope. What about a zero slope and an undefined slope? Well, a zero slope is what we call a constant function. Right there. That's our constant function. Slope of 0. I can handle that. I can walk across that line. Zero slope. Undefined slope, however, that I can't. I'm nothing. I got nothing for that. That's not even a function. Undefined slope is a vertical line. Constant function is a horizontal line. Slope is 0. Undefined slope is a vertical line. Slope is undefined. It does not exist. Okay. How do I figure out what slope is? Well, slope is rate of change. So let's put that down. My slope is rate of change. And when I have a straight line, it's a constant rate of change. I can also think of slope. I use the variable m to represent slope. I can think of it as change in y over change in x. Delta is that triangle symbol, Greek delta. Change in y over change in x. So I'm looking at the difference in my y-coordinates compared to the difference in my x-coordinates. I also think of slope as rise over run. Those are ways to find and calculate slope. So if I am interested in this line, I see that this line has a negative slope. It's decreasing. So I expect when I find m, the m will be a negative value. M is going to be change in y's compared to change in x. I'm looking at these 2 points. These 2 points are on my line. I've got y values of 6 and negative 7. Change in y, I've got to pick a point to start with. It doesn't matter. I'm going to show you that it doesn't matter. If I start with 6, I say 6 minus a negative 7. If I start with negative 7, I say negative 7 minus 6. Notice I'm subtracting the second coordinate, whichever that coordinate might be. Now, if I started up here with 6, when I move to my x coordinates, I've got to start with its x value. So I'm going to say negative 5 minus 4. Where I started with negative 7, I have to start with its x coordinate. So I would say 4 minus negative 5. Okay, so what's the slope of this line? Well, 6 minus negative 7. If I'm subtracting a negative, I add the opposite. That becomes 6 plus 7. That's a positive 13 over a negative 9. Negative 5 and negative 4 is negative 9. Or negative 7 minus 6 is a negative 13 over 4. Subtract a negative, add the opposite. That becomes a positive 9. Now, when I do division, if one is positive and one is negative, the result is negative. So my slope for this line is a negative 13/9. I can put the negative sign in front of the fraction bar, in front of the denominator, or in front of the numerator, and it means the same thing. Okay, I'm sorry, I apologize for the cough. Let's talk about domain, range, and families of functions. Domain, range, and families of functions. Now, we've already kind of introduced domain and range without using those terms. Domain is my set of x values. I mentioned when we set up our graph on the first page of notes that was our independent variable. I misspoke and said it the wrong way to start with. It's our independent variable. The domain we can also call our input. The range of the function is the set of y values. We would call it the dependent variables. Whatever y is depends on what we start with for x. And the output of our function. So if I reference a function value, I'm talking about the range. Now, In the past, you've probably been taught to graph by coming up with a bunch of points. But we are going to focus this semester on graphing using transformations based on families of functions. Families of functions are different types of functions and their graphs, and the sooner you memorize the shape of these families of functions, the general shape, the easier life is going to be for your graphing. Types of there's my first, there we go. Oh, and I don't have an erasable pen. Let me just do this. Types of functions and their graphs. The most basic of each family is the parent function. Most basic is the parent function. And then you apply transformations. You apply transformations. Now we're going to be focusing, again, I said this once, we're going to say it again, we're going to be focusing on parent functions and transformations when we graph, not in using a calculator graphing tool or plotting multiple points. That should make you take in a huge sigh of relief because it's a lot less work intensive. Alright, here is how it is going to work. Now this page, this is your family of functions page. This is your friend. So make sure you have this filled in and that you keep it handy until you get these families of functions memorized. Okay, now where I draw these functions, for the parent function, it matters. So yours needs to match mine. On the last set where we just did slopes, it didn't matter. I just wanted an example of each of these types of slope. For this one, for the parent function, location matters. My linear parent function is y equals x. That is the line with a positive slope, a slope of 1, that goes through the origin on your graph. So I'm going up 1 over 1, up 1 over 1. My slope is 1 here for this line. Positive 1. M is 1. Very sloppy M. This pen erases. Okay, M is 1. The domain, you see I have arrows going both directions. My domain is all real numbers from negative infinity to positive infinity. And my range is also all real numbers. It keeps going up and down, left and right forever. That's what the arrows mean. Quadratic function, y equals x squared. Hopefully you remember quadratic functions. Any squared function gives you a graph that is a parabola. Now this parabola, when I do stuff to make this equation bigger, different, as long as it's x squared as the base, it's going to be a parabola. That parabola could get stretched, it could get squished, it could get flipped upside down, moved around on the graph, but it's still going to be that parabola shape. My domain of my parabola is all real numbers because it goes out forever from negative infinity to positive infinity, but the range has a limit. As I read my range, I'm moving from the bottom up, from negative infinity up to positive infinity. And I see that my parabola doesn't start till I get to 0. So I have 0 included, square bracket right there, all the way to positive infinity. My infinities, I always use curved parentheses because we never get to infinity. It's always out there somewhere. So my quadratic function has a domain of all real numbers, but the range is going to have a limit. That limit will depend on if I take this function and have it sitting at 0 or if it gets shifted up or down. Cubic function, my parent function that is the cubic function, y equals x cubed, sits with a twist on the origin. It is an increasing function, a positive function. It moves, starts low, finishes high. You see I have arrows on both ends. It's moving up. It's also moving out. So my domain and range, all real numbers. Absolute value function is what we would call our first piecewise function. We will get to later on, piecewise functions. But the absolute value function, those absolute value bars right there, mean you have a V-shaped function. Parent function looks just like that. Again, domain, all real numbers because it continues left to right forever, but my range has a limit. My function doesn't exist down here. For my parent function, my function doesn't start until I get on the y-axis to 0, so my range is 0 to infinity. Square root function is the inverse of my quadratic function. Squaring something and taking the square root are inverse functions of each other. I have a half parabola that lays on its side. Now you can picture, I would finish out the parabola, it would be down here. But we don't finish out the parabola because if I finish out the parabola, it would not be a function. So we choose to limit that, and we'll talk more about that later. But basically you have a half parabola, it's the upper half in quadrant 1, starts at 0. Now, domain and range have a limit here. If I'm reading on my x-axis, it doesn't start till I get to 0. That's 0 inclusive. If I'm reading on my y-axis, it doesn't start till I get to 0. So both domain and range have limits for my square root function. For my cube root function, it is the inverse of my cubic function. So I'm going to take this cubic function and lay it over on its side. When I do an inverse, it actually reflects across this line, y equals x. For the cube root function, that ends up looking like my cubed function laid over lazy. It is a positive function, it's increasing. Doesn't have a slope because it's not straight, but it's increasing as I move from left to right. Arrows on the ends show that my domain goes on and on forever. It's also going up and down, so my range is all real numbers, negative infinity to positive infinity. Now, like I said, we're going to be using these parent functions to graph, so you're going to want to keep this handy to be able to reference the shape of these families of functions until you get comfortable with them. Now this first video is going to be a little bit longer because we've got a lot of information here at the beginning of the semester to try to introduce. So hang in there with me, guys. We're going to probably have about another 15 minutes of the video. We're going to emphasize our pattern of transformations. Now we've introduced our families of functions, and I've warned you that you don't have to find a whole bunch of points to graph. You also cannot use a graphing calculator. Let's make a note of that. Graphing calculators not allowed. Don't use them on your homework because you can't use them on the test. Okay, graphing calculators not allowed. Just a scientific calculator like this. I highly recommend you get one like mine so that your buttons are where my buttons are and they do the same things. Okay, here we go. Pattern of transformations. This pattern of transformations works for all families of functions. Works for all families of functions. And I mean all. You use the same pattern of transformations in pre-cal when you're graphing trig functions. So that is always going to hold true, that you've got the same pattern of transformations. Now, you've got your function f of x. Over here, f of x is the same thing as y. So this function value of x emphasizes that x is our independent variable. We plug it in and we get out y, which is our dependent variable. This is the same thing as y, my function value. I have my x over here, and I have 1, 2, 3 variables that that are going to change things for my function. So the first one we're interested in is this h here. H is for horizontal. Horizontal is across left to right. This is my horizontal shift. So I'm moving my function left or right. And notice that it starts with that negative there. That's really important. Starts with a negative. Now why is that really important? Because if I have an expression right inside parentheses, I have an expression that says x minus 3. That x minus was already there. I plugged in a positive 3. Well, if I'm moving my function left or right, which way do you think that positive 3 is going to go? Well, it's going to go to the right. It moves 3 to the right. But positive 3 looks like x minus positive 3. If I plugged in a negative 3, that would become x plus 3. It goes the opposite way you think. This is going to go left because I actually plugged in a negative 3 here. This would go right 3 units. This one would go left 3 units. Those are two different examples. Okay. That's my horizontal shift. H is for horizontal. Now K, I don't know what K stands for, but it represents our vertical shift. Vertical is up, down. And notice that it is plus K. So it's going to go the way you expect. It's going to go the way you expect it to go. If it's plus 3, I've moved it up 3. If it's minus 5, I've moved it down 5. Okay, the other variable we have here is this A out front, a coefficient out front. This is going to give me either a stretch or a shrink. Now, we don't care if it's positive or negative. What we're interested in is it a whole number greater than 1. So I'm going to say absolute value of A greater than 1 to whole number. That's going to give me a vertical stretch. Like I grab the ends of my function and I pull them apart. If that value A, not positive or negative, just the absolute value of A, is less than 1, if it's a fraction, it's going to give me a vertical shrink. And I think about grabbing the ends of my functions and squishing them in together. Okay. What about if it's positive or negative? That's something that's important to consider as well. So if I have a negative out front here, a negative out in front would cause it to reflect across the x-axis. Reflect across the x-axis. So it's going to flip it upside down. If I had a negative inside here, that would cause it to reflect across the y-axis. That would flip it this way, left to right. Okay, now you'll notice I have just this little box here. That box is whatever my function is. So, not function value, function, type of function. Function type. There we go. That box represents my function type. It can be squared, cubed, square root, cube root, absolute value. The horizontal shift is attached to x because x is my horizontal axis. My vertical shift is tacked on at the end. And then I've got my stretch or shrink here out front as a coefficient A. Now, let me grab something real fast. To help us visualize this stretch shrink thing that I'm talking about. So, okay, here is my parent function parabola. If this coefficient A is a 3, it's a whole number, it's positive, that's a stretch. That means I take my parabola and I stretch it out. Well, when I stretch it out, it gets skinny. If it is less than 1, let's say A here is 1/2 or 1/3, I think about shrinking it, I think about squishing it. And when I squish a parabola, it's going to open up wider. So that's what I mean by a vertical shrink. Another word for shrink here, for vertical shrink, would be a vertical compression. And it can be easier to picture it as being compressed and opening up wider. Okay, let's get through these examples of some transformations. Again, we're going to, if you have me in class in person, we're going to work more on this in class. If you happen to be all online, you're going to have to go figure out some more examples or work through it in my math lab. Graph the parent function with a dotted line or a color. We're going to use 2 colors, and I'm going to graph the parent in green. Then we're going to figure out the transformation, and we're going to graph the transformed function in a second color. Okay, here is my function, y equals x minus 4. Well, this is not a parent function, but it's got those lines. Those lines represent absolute value. Absolute value parent function is a v centered on the origin opening up. Parent function right there. There's my parent. Y equals absolute value x. My transformation is happening right here. So I look up here and I say, okay, well, that's inside the absolute value bars attached to the x. That's a horizontal shift. It's going to move my function left or right. It starts negative, x minus. It's still x minus. So what I plugged in here was a positive 4. So that's going to shift my function 4 units to the right. So I'm going to take my v and I'm going to shift it over 1, 2, 3, 4 units to the right. and it's going to open the same distance, the same v shifted 4 units to the right. Okay, now I need to answer questions about my transformed function. Answer the questions about the transformed function. Y-intercept, I don't know. But I do know that the y-intercept happens where x is 0. So if I go up here and I say, okay, y equals absolute value 0 minus 4. Well, 0 minus 4 is negative 4, but the absolute value means distance units away from 0, and so that always comes out positive. So my y-intercept is 0, 4, 1, 2, 3, 4. There's my y-intercept, 4. That's sloppy, sorry. Zeros are the same things as my x-intercepts. X-intercepts happen when y is 0. Well, that's that point right there on the x-axis for 0. Domain and range, I see that my domain of my parent function, domain is all real numbers. Once it starts as all real numbers, it stays all real numbers. Range has a limit. For parent function, its limit is 0. I moved it I moved it to the right. I didn't move it up or down, so my range is still from 0 to infinity. In behavior, what happens as I go on forever with x to positive infinity or negative infinity? Well, as x approaches positive infinity, y values are going up. Y approaches positive infinity. As x approaches negative infinity, as I move back to the left, y is still going up to positive infinity. That's my end behavior. Okay, let's do another. Parent function, that is a square root right there with a coefficient out front. So let's find our square root function. There's my parent. Let's graph the parent. Half parabola opening out to the right. That is y equals square root x. That's my parent. Now let's do our transformed function. Well, I've got this coefficient in front of my square root symbol. That's a value a. That's either going to be a stretch or a compression, stretch or a shrink. Well, it's a whole number. It's greater than 1. 3 is greater than 1. So it's going to be a vertical stretch. By a factor of 3, times 3. Vertical stretch by a factor of 3. So it's like I take my function and I stretch it out. Well, what's going to happen if I stretch it out? This origin point is going to stay put, and this is going to stretch upward. So it's going to kind of straighten it out and stretch it out like that. Okay, x and y intercept for the transformed function, it's sitting on the origin, 0, 0. That's both x and y intercepts. There's my x-intercept is a 0. That's another name for the x-intercept. Domain, limit. X values start at 0, go to positive infinity. Range, y values start at 0, go up to positive infinity. In behavior, I only have one end. This has a limit. This has an end. So as x approaches positive infinity, I only have one limit. As x approaches positive infinity, x doesn't go back to negative infinity. It's limited over here. So I only have one in behavior. As x approaches positive infinity, my y values are increasing, so y is also approaching positive infinity. All right, excellent, excellent. 2 more examples of transformed functions. Keep your filled-in pages handy. So first we identify the parent. This one has a little 3 as an exponent. 3 is an exponent. That's a cubic function. I've got this as my parent function right here. This little curve, kind of a backwards S curve, I always think of it. I've got a couple of things going on. I've got a negative out in front. Oops, that's a transformation. I've got a negative out in front, and I've got a 1 added on. Well, that negative out in front tells me it's going to reflect across the x-axis. It's going to go upside down. This 1 tacked on, it's not being cubed with the x. It's not inside with the x. It's tacked on at the end. That is a vertical shift. It goes the way I expect. It's a positive, so it's going to go up 1 unit. I have 2 transformations for this one. So I'm going to think, all right, I'm going to take my little curve, my little cubic swish. I'm going to take this vertex, this pivot point, I'm going to move it up 1 unit. Go up 1 unit. And then I need to flip it upside down. So instead of starting low, finishing high, I'm going to start high, I'm going to finish low. There's my transformed function. All right, y-intercept is easy. I moved up 1, so I am at 0, 1 for my y-intercept. To find the 0, or the x-intercept, I set it equal to 0. I set y equal to 0. So I say 0 equals negative x cubed plus 1. I subtract that 1. I've got negative x cubed. I divide by a negative because I got to take care of that negative out front. So 1 equals x cubed. The inverse of finding the cube of something is to take the cube root. Don't worry about this. This is a lot. We'll talk about how to do all these algebraic processes when we're together. Or you can Google or do Khan Academy videos on it. What times itself 3 times gives me 1? Well, that's just 1. So x would be 1. So the x-intercept is 1, 0. Domain and range, if I look at my parent function sheet, domain and range for my cubic function, all real numbers for both of them. If it starts all real numbers, it stays all real numbers. Never changes. All right, this last one in behavior. Well, domain and range are both all real numbers, so x gets large in a positive direction, x gets large in a negative direction. What does y do? Well, as x moves in a positive direction, y is going down on my transformed function. So y is moving to negative infinity. As x gets large in a negative direction, as x approaches negative infinity, y is going up. So y is approaching positive infinity. Again, throwing lots of examples, lots of information at you. Figure out what you understand and what you know. Follow it along and write down the rest, and prepare to ask questions about it when we meet together. All right, pause the video. Figure out the parent function for this one and what's going on for the transformations. We've got a negative out front. It's going to flip it upside down across the x-axis, and it's going to shrink it. It's going to compress it by 1/2. Remember we said what happens when we take our parabola and we squish it together? Well, it gets fatter, it gets wider. So when I flip it upside down and sketch that compression, it needs to visibly be wider than the original. My x and y intercepts sitting at the origin, they're the same. Domain for my quadratic is all real numbers. Range has a limit. The transformed function, the range is 0 to a positive infinity, but I flipped that upside down. Now I'm starting down here at negative infinity, and I'm going up and stopping at 0. Anytime you give an interval, I got to talking and I wrote it down wrong. Anytime you give an interval, you go from least to greatest. So I start at negative infinity, I end at 0 inclusive. What happens as x gets large? As x approaches positive infinity, as x approaches negative infinity? Well, both ways, my y value is going down. So for both directions, y is approaching negative infinity. It's moving downward. All right, last section down here. Write the equation of the function with the given transformations, and then sketch a graph. So it gives you the parent function and tells you what we want to do, and then you need to write the equation and graph it. Well, parent function, cube root x. Parent function for cube root is right here. My pattern of transformations, moving to the right, that means I'm plugging that value in here, and down 12 means I'm tacking it on at the end. So I'm taking my function, horizontal shift is underneath this cube root symbol attached to the x. It's moving to the right 5 units, so it starts as x minus a positive 5 moves me to the right. Down 12 units, not underneath the cube root symbol, I have a negative 12 out here. Shows that I'm moving down. So I've got over 5 to the right, down 12. My parent function, cube root would be right here at the origin. I take this origin point, over 5, down 5. That's my shift point, but it's still laid on its side. My parent function would be right there. Wow, equals cube root x. This is my transformed function. All right, what about this one? Square root x. We've done a square root. What transformations do I have here? Well, I'm reflecting it across the x-axis, and I'm stretching it by a factor of 3. So y equals reflect across the x-axis. That referencing over here, my pattern of transformations, that's a negative out front. I have a stretch, a vertical stretch. That means my whole number goes out front for this value a. So my equation is going to look like a negative 3 square root x. I haven't moved it away. So my parent function would be right here. Y equals square root x. I'm flipping that upside down and I am stretching it. So I'm pulling it out. So it's going to start at the same place, it's going to go down, and it's going to straighten out a lot. So there's my transformed function. All right, last problem. You guys are doing great. Hang in there through this last one. We should have arrows on the ends of that parabola. It's a parabola. What type of function gives me a parabola as my shape? Well, that is going to be a quadratic function. My quadratic function, y equals x squared, is the parent. What have I done to that? Well, my vertex isn't at 0, 0, it's over here. So I moved my vertex to the right 3, and then I moved my vertex up 2. So I have a horizontal shift and I have a vertical shift. So when I think about my pattern of transformations, I have a horizontal shift, plugging in a positive 3, and I have a vertical shift. So I have y equals x minus, and then my shift to the right is 3 units squared because it's quadratic, and then it needs to go up 2, so plus 2 for my vertical shift. All right, excellent, good job. Make sure that you maybe take a look at your My Math Lab homework, but bring these to class with you.